Hi. This is a kind of a newer package. I developed it over the course of the last year and a half or so, 2 years almost. And it's outgrowth of funding from DARPA, from DOE, and subcontract to the Brookhaven National Lab. I developed it for two particular reasons. One, the DOE funding that I have is on exascale computing, basically designing an exascale computer. We work with a lot of the large companies like IBM and Cray and whatnot, and the goal is to be able to run material science simulations at the exascale, so then the hardware companies and software companies know how they need to develop out the machines that they're going to end up selling to the government. And the other part is I'm a materials scientist, or at least I was at some time. And one of the things that I wanted to be able to do was, in a very easy way, discover what a potential energy surface looks like for an unknown material, right? And so that is a pretty nasty thing to do, but it's also a very general thing to do. And so I have a lot of, I have a kind of a history of building optimization code and parallel distributed computing code. And this was part of my parallel computing package that I've put out into a separate package by itself, and it's exciting. The exciting thing is that there's a unified API for storing things in memory, on disk, in a file, or in a directory of files, or in a database, or in a database table, or other type of things like HDF5 files. So basically, an abstraction that works with anything you're going to do key value storage. Before I actually get to the riveting parts of that, I think the better thing to do is to start with a good motivating example to show why this kind of thing is useful, right? So here is, I actually was able to implement a generalized n-dimensional search. So generalized n-dimensional search, where here I'm going to target all of the unknown functions, minima and maxima. So basically find, if I was looking at a material, I would find all the materials, local minima, global minima. So then you can get a picture of what the potential energy surface looks like. And then build a fast proxy function to interpolate the potential energy surface, so you can call it as an analytical function. So that's, I kind of, if I have time to come back to it, I'll go through the code here, but it's basically an ensemble solver, which comes out of the Mystic package, which launches a number of optimizers at the same time. Buckshot is like a shotgun, and it throws a bunch of optimizers out, and a lattice solver grids up space and lets things go. And then I have local solvers. So these are very dumb solvers, right? They're very localized solvers, but I'm solving a global optimization problem with these local solvers. Because I basically want to throw a bunch of balls at the space and have them all get stuck in the local minima. And then here's my parallel computing package, which basically says I'm going to run this on multiple processes if I can. And so I'm going to run all the optimizers in parallel. And then there's this is the setting up of the optimizer, where it has a mapper, and the mapper is what makes it run in parallel. Down here, there's a memoization step, which uses Klepto. So basically, I picked Klepto's infinite cache because I know there's not going to be too many local minima on this. Just by knowing the function, I'm running some test functions. They have like standard nonlinear test functions of, maybe anywhere between 5 and 100 local minima. I set up this cache, and so this is what we'll see later. I'll explain parts of this later, but this is basically setting up a cache with an archive backend. So a cache is a memory cache, short-term fast access memory, where when you call a function, you can look up in localized memory, and it saves you time for reevaluating it. And then it has an archive backend, so whatever your archive backend is, in this case, I'll make it a file system directory, I believe. So it's a bunch, each entry is a file, and it's separated out over a directory. But it could be a SQL database or HDF5 file or something like that. And there's the encoding steps, and I'm ignoring all of the keyword arguments, and I'm ignoring whatever I pass in as out. So we'll see a little bit more of how to do that. And basically, I hook up the cache to the memo function, and then run the solvers, and then dump the trajectories and the results. But I only am dumping the results because I need to get the results out. Later, I'm ignoring it in the cache. Don't worry if you don't follow all of this. We'll get to actually the details of the Klepto a little bit later. So, and then this is basically setting up an optimizer. Here's configuring Klepto to use a backend, an archive of a directory, where I'm just naming it the same name as the model, and I'm setting up the directory to be used serialized files. And in this case, don't use a caching intermediate. So all of my archives, all of my caches or archives, you can say use short-term memory or just work directly with the backend. And you can control the size of all of them as well. So here's the loop. It's basically I'm going to run optimizers. So I throw something like 25 optimizers at the problem, and they all trying to get stuck in local minima. And then I throw optimizers at the problem again, 25 more, and they get stuck. And it keeps going and going until so it's cached. And I can check hits and misses in the cache. And so I can say, keep running until n number of misses, or whatever condition I'd like to pick. So I chose here, just to keep it simple for the demonstration, keep running until there's 2 runs where there are no cache hits, so where there are no new points found, right? So there's no new points found, which means I probably did not find all the minima, but I could make it run for 9 or 10 of them, and then I would definitely find more of everything. So then after it goes through and just keeps throwing optimizers to try to get stuck, then it basically stops and prints out the minima. And okay, so that's search for the minima, search for the maxima, and then after it, we just do an interpolation. So I take the trajectories and do kind of a standard. Where's the part? I do an interpolation in the SciPy RBF radial basis function there. Okay. Some of these files, if they get a little big, I just do a little downsampling on points because I don't want it to take too long for the demo. And then at the end, now I have this function that's a proxy for this potential energy surface. And I can test it to see if it has the same minima and maxima. I know what the minima and I know what the maxima are. And I can save that function that I just built, this RBF function from SciPy. I can save it down here. So I'm plotting the thing just to show what it looks like. And then I can save the thing in a file archive called models pickle, again serialized. And that's going to save this proxy function that I built off the interpolation. So just to give a taste of what this thing looks like, let's see. Okay, so that's the function I'm going to be working with, the Grewank function. It looks like that, right? So this is what we're looking at. And a lot of times people's strategy for building these kind of functions are what they would do is a grid search, right? So they would just make a grid and then interpolate off of points on the grid. But that doesn't work very well because you miss the critical features, which are the turning points, the global minima, and the global maxima. But an optimizer, that's the places an optimizer traces, right? It traces after turning points. There's a lot of points around minima, maxima, and turning points, especially in Mystic where you can set it to do that. So here it took a bunch of times. There was 2 places where there was a miss in a row, and I got 17 minima. And then we basically can look at the picture. I'll do it in 2D so you can see all the blue points are the minima, and you can see there's the trajectories going down into the minima. Okay, it hit all of them. And then we do a search for the maxima the same kind of way. And we interpolate. And I'm doing some, just to make it fast, some fairly cheap interpolation, so it may be a little bit fuzzy as far as what there could be a little messiness in the points, but hopefully it looks almost identical to the function we saw before. The nice thing about it is they're all the same heights. All the minima and the maxima are the same heights, which is exactly what it was, even on the ends, right, where interpolation could be nasty. So it's a pretty darn exact match of this function where it's pinpointed basically the minima and maxima. And you can see here the minima is 0 and the maxima is very close to 0. And the maximum, it also got pretty well exactly too. Then I can take this function here and basically I have a file that's holding on to the function I interpolated so I can use it later, basically. And now I don't have to calculate the expensive things. So the idea is the first thing I was doing, I'd probably run in some massive parallel, and now I have a cheap function that I use that mimics the thing exactly. So how does this kind of happen, right? And oh, by the way, you can do this for harder functions, right? So there's like this one, right? This is harder because all of these points are little local minima, and it's found these features too, right? So this function has minima here, here, and there, but it's able to do that well, and this one, there's a lot more points, so it'll take another second. So I'm actually going to wrap this up. This is right now not in a very functional code, but I'll just wrap it into part of the Mystic package as a function call you'd make. And he should come up in a second. Like there was a lot more points on this one because it's got a ton of points. Well, yeah, there we go. So I was even able to capture all of the minima on this function, which is pretty nasty, right? There was something like 60 local minima, and even with the cheap interpolation, it covers the points pretty well. This is a standard nonlinear test function. All right, so now we'll get to the exciting part. Like I said, the use of Klepto. So here's basic use is you have a you say Klepto, I want a SQL table. It can use SQL alchemy, so you can pick any kind of, you could say MySQL, give your location, and say cached or not cached. Cached means, again, local memory. So do you want a local memory buffer first, or do you want to interact directly with the backend? And so I can basically pickle any object, or there's several different kinds of pickling. You can use JSON, DIL, Python, HICL, which is HDF5 pickling. It's a mix. It uses DIL and it uses HDF5 for the objects it can work with HDF5 on, and you basically can choose your serializer. And so here I'm sending a lambda, the max function, 1 and 2 to a SQL database, a SQL table, and then I'm extracting them from the so it's max squared 2 comma 1, and you see I'm calling it directly out of the SQL database, and there I get 4. Here is building a directory archive, and I'm going to go through some NumPy stuff. You can see I'm saving an array, a big range, a data type, a compound data type that you might use in a structured array. So the NumPy inf, the NumPy point-to-point ufunc, and it basically, that sucks. And it basically does okay. I think I may have just had a freeze. Let's see what I can do. Do you mind if I unplug this and see if it comes back to life? If not, I'll do my best without. Okay. So what we could do maybe is I'll reboot this and we do questions first. Okay. So let me say just a couple more things. All right. So it basically, oh, that's a bummer. It can abstract. As you can see, it can basically take any object that DIL can serialize. Basically, can be sent to any of these caching or archiving backend. And it allows you to have abstractions on the different types of if it's fast, it'll come back up. There's going to be a lot of problems here anyway, I think. It allows you to have abstractions not only on the archives, what kind of archive do you want in the background, but the abstraction for strategies communicating between the memory cache and the archive itself. So you can say, there's a standard in Python, the LRU cache, least recently used, right? So basically what it does is you say what size of a memory cache you want, and then the ones that are used the least are depopulated, right? So you can choose to depopulate them to the void, a null cache where they go away, or you can choose to depopulate them to the archive. So basically, things are held in memory cache, and then when something's not used very much, it gets pushed in seamlessly to the archive behind it. And and you can set an option for, do you only want to look in the memory cache, or do you want to look in the memory cache, and if it's not there, go and fetch it from the archive? There's that kind of option, and you can pick the different strategies. So it's not just LRU. There's a random loss strategy. Most recently used, I have about 5 or 6 strategies that you can pick from. And not only, so what you didn't see very much, you saw a dictionary interface. It also provides a decorator interface. So you decorate a function, which you saw a little bit in the in the first part, right? So you can decorate a function, and basically it caches as the key. It caches a cryptographized version of your inputs, and it stores the value as the outputs. And so I can pick. I have several levels of cryptography. I can use serialization of the object, and it's big and nasty, but it's unique. I can use ID, so that's a quick hash, a Python hash. I can use MD5. I have all sort of different encodings, string encodings. There's about 30 different cryptographic hashes that you can use as your unique identifier. And it automatically will use those as your keys. And you can look them up. It has a translation service for, if you give it your inputs, it'll translate it into the cryptographic hash, look up the value, and retrieve it from the database or whatever you have as your backend. I also have a validator, which enables you to check if the function, if the inputs you have would work or not, right? So you don't want to pass bad inputs and potentially create bad keys and bad values that are stuck in your database. So you can put validation on, and what it does is it digests the function's signature. So it can tell you, even through things like multiple partials, right? What variables are the args and the keywords, if it takes args and keywords, and even things that, Python lets you double dip on a few things, like if you have a y as an arg and also as a keyword, then it blows up, right? So what it does is it knows the function signature, it can validate whether or not it's a valid input, and it'll throw the same error that the function would throw if it were called, and let you see that error. But if it succeeds, it doesn't call the function. It basically passes a none and says it's okay, and then when you call with call underscore call on your proxy object there for the function, then it evaluates the function. So all my caches use that, so you can have a safe cache or not. All right, so it's up on GitHub on the UQ Foundation site. I appreciate it. I'll put this talk up. Unfortunately, it crashed and I didn't get to the last bits of it, but happy to answer questions. Yes, Chris. You can do that if you have cache. You can set anything you like up as a cache, and these caches can be shared and cloned and passed around. They're all serializable. So you know Mystics Optimizer is serializable, but these caches are all serializable too. So I can take a cache as a dictionary or something else and then pass it around to other processors and have it populate local caches over there. So one of the things that I'm doing now is doing cache backend synchronization. So you have database to database synchronization by passing the caches and archives around as serialized objects. That allows you to have distributed data basically, but that's still work in progress. But what you're asking is the use cases. I think so. People may not. Mystic is my optimization package, and the use cases are essentially for Mystic. I don't want to reevaluate expensive functions, and also it has a nice feature called rounding. So I implemented cache rounding. Several types of, there's a few different types of interpolation, but the one that's the most important for caching is if you make a bubble around any inputs that you evaluate, right? So if you're doing optimization, you might have little, 1e to the minus 6 changes along the way, and you don't want to have it cache every single one of those little changes where it's just a slightly different answer. what you actually might like is to set the size of a ball, and then anything that falls within the size of that sphere in the database is not reevaluated. It's just looked up, right? So that actually makes a huge difference in speed. You're able to have an optimizer or something else keep sampling off a database, and if it falls within a sphere of a point that's already there, then it just returns the answer to you. So I use it to speed up a lot of optimizations, and I allow process-to-process communication through these caches. Not all caches can be have multiple parallel pointers into them. So some can, like HDF can. A SQL database can. It's a file, right? A file can have multiple pointer access into an HDF5 file, so you can do parallel access on one of those things. Yeah. So generally what I do is I write to a cache, and it's the cache's responsibility of writing to the archive, right? So if you have a parallel problem where you need locks and those kind of things, it's not the user's thing to worry about that. It's the cache and archive. I have a sync step that says synchronization, where you can control how it writes to the archive. That's right. Yeah. What do you mean by that? I do not have a. Yeah, can the rounding work dynamically? I don't see why it wouldn't, but I basically implemented a independent rounding decorator that when you give the size you want to round to in tolerance, then it just rounds to that tolerance, and it actually rounds down through the stack. You can either shallow round or round through everything that's afloat, but I don't have it, so you can dynamically pick the size. Everything is abstract, independent objects here, so you could build one of those and then use it with the rest of the infrastructure.